We're going to talk about 3D free body diagrams. We're going to talk about equilibrium equations in 3D. We would actually take a look at some of the constraints and the condition of the supports in a three-dimensional statics, and statically determinacy would also be discussed. So we're going to concentrate on pretty much three-dimensional statics today. The objectives are identify support reactions in 3D and draw a free body diagram and apply the equations of equilibrium. As such, activities are listed here: reading, quiz, applications, support reactions in 3D, equations of equilibrium, concept quiz, a group problem solving, and we are going to wrap our session with an attention quiz. So let's go over this short quiz. Number one, if a support prevents rotation of a body about an axis, then the support exerts a blank on the body about that axis. So obviously, if a support prevents rotation, and that means that there will be a couple moment exert on the body about that axis, and the answer is a couple moment. Number two, when doing a 3D problem analysis, you will have blank scalar equations of equilibrium. The answer is 6 for the reasons that you would see. Remember that we are going to take a look at the three-dimensional analysis today. Some of the applications of what we would be covering today is in like ball joints and also journal bearings. They are often used in different applications, and of course, in order for us to design it, we need to know what would be the reactions of the support at each case. Other applications, one is shown here in buildings. For example, in this case, there's a tie rod from point A. It's used to support the overhang at the entrance of a building. I would never design a building like that, but some designer decided to do that. It is pin connected to the wall at A and to the center of the overhang B. Now, why I wouldn't design something like that? Because there is no redundancy here, and I'm not very comfortable with systems that doesn't provide much redundancy. But this is a decision of, I'm sure, the engineer that were involved in the process. So if we move A to a lower position, D, would the force in rod, which would it change or would it remain the same? If we make such a change without really looking at the engineering aspect and engineering calculation of it, it may lead to catastrophic failures. Also, another application in 3D is a crane that's shown here in this figure. This crane supports a 350 weight of the oil drum, and how would we actually find what would be the largest weight that the crane can support without overturning? Because again, remember, the results could be really catastrophic. So let's take a look at the support reactions in 3D. This is one of the tables of your book, depending on what version you have. It may be 5.2, it may be other table, maybe named differently. So let me just take this out, makes it easier and subject to less confusion. So a few examples are shown here. The support reactions are too many to be shown here, but we can pretty much look at it here. As you can see, this is the number 2 is a smooth surface support, and the rest are shown here. This is a ball support. single hinge and the single journal bearing. And as such, when you see this red kind of like a circular arrow, and that shows the moment, and the forces are shown in the direction in which they are shown. For example, for a single hinge, we are going to have, of course, three forces, three reactive forces, F sub x, F sub y, and F sub z, and there will be two moments in two direction that the hinge is prevented from moving. For a ball support, it is free to rotate in three direction. It only has constraints against the translational movement. As such, F sub x, F sub y, and F sub z would be the only forces that would be the only three reactive forces. Okay. So it's important to note that sometimes a single bearing or hinge can prevent rotation by providing a resistive couple moment. Now, it's also important to realize that only force reactions could be generated, and there could be no moment reactions created. So everywhere we have forces, it doesn't necessarily mean that a moment reaction would be created. Take a look at the first case up here, the one that supports a 500 Newton downward force and a moment of 45 Newton meter of the moment that's shown here. If you want to draw the free body diagram of such a situation, at C, there will be two C sub x and C sub y, and A would be A sub x and A sub z and A sub y, depending on the reactions and whichever direction that it is prevented. In this case, x is in this direction, and y and z is also shown. So this is actually the direction of the x. So x, y, z are shown as such. And again, for example, in this case, A is pretty much free to move in the x direction. As such, the reactions would be only in the y and z direction, and so on. Let's take a look at this other case here, the 400 pound that's applied to the structure as shown. If we take a closer look at C, we would realize that C is actually can rotate in all directions because of the way it's being provided, but it cannot go through any kind of a motion, so it's prevented from moving in the X, Y, and Z. As such, we're going to have three component of the reactions at C. And if you look at, for example, support A, in A, again, it's free to rotate, but it's not free to translate in two directions, and that is in the Z and X. It is free to move in the Y direction that's shown here. So as such, we need to examine our structures before we can determine with a high accuracy what will be the reactions at the support. So as we stated earlier, again, when we have a body in equilibrium, the summation of forces is zero, and the summation of moment about any point on the body or any arbitrary point should be zero. It could also be outside of the body. So these two vector equations that we know here, summation of F and summation of moment, they could be written in 6 scalar equations because we are now dealing with 3D. And in 3D, you could have summation of forces in the X, in the Y, in the Z, and the summation of moment about X about y, and about z are said to be 0. So these are the 6 scalar equations of equilibrium that we would be dealing with. And again, the moment can be determined about any point. Usually we try to pick up a point like we did in 2D, where the maximum number of unknown forces are present. It's going to simplify the solution. Again, it requires some practice to be able to do that. So what is statically indeterminate structure? Again, in most of our structures, we would try to provide as many redundancy as possible in case one member fails, the other member can pick up the load, and primarily that is for safety and reliability reasons. As such, when a body has more support than necessary to hold it in equilibrium, it becomes statically indeterminate. Let's examine the figure here and try to determine if this is a determinate or indeterminate. We have 6 equations of equilibrium available in scalar form. If we have more than 6 unknowns, then the structure is indeterminate. If we have less than 6, and then we are determinate. It's as simple as that. Are they used in practice? So we already answered that question. And the reason is pretty much for safety, and also for pretty much safety is really the bottom line. Okay, so an example here, we have 6 unknowns, but there is nothing restricting rotation about the AB axis for this particular structure. In this case, the summation of moment about AB is not 0. A structure like that would move under the application of load P. It's going to fail right away. And I've seen sometimes some of these computer games that are not very realistic. They have some of these members of a game that when something struck them, it just failed right away, which statically that's impossible to occur. So that's one application of where some of these computer games that everybody nowadays play, they pretty much not as accurate as possible. Also, examples could be in some of the Hollywood movies. Although most of them are pretty good, in some of them you see that something happens that doesn't really make the structure to fail, but it would fail. So those are just typical day-to-day examples that we all deal with in a movie. So we have 6 unknowns, but there's nothing restricting rotation about the AB axis. What about this other case that is shown down here? We put that in the category of some cases. Again, in this case, the summation of moment about an A is not going to be 0. Again, under the application of load, the structure is going to become unstable and it is going to fail. Okay, so let's take a look at a great example here. The rod is given. It's supported by a thrust bearing at A and a cable BC. It's subjected to an 80-pound force. We would like to find the reactions at the thrust bearing A. So at this point we are after the reactions, and we would like to find the reaction in cable BC, shown here in red. So our strategy, we're going to establish an XYZ coordinate. We're going to draw a free body diagram. We're going to write the forces in scalar form, and we would apply the scalar equations of equilibrium to solve for the unknown forces. So the free body diagram of the rod is shown here now, and as you can see, there would be all reactions would be shown here. At cable BC, there will be force BC in the direction of the cable. The cable is pretty vertical. The 8 pound is shown here. we put x, y, z coordinate, the origin of the coordinate system x, y, z, right at A. If you put them at other locations, would it be possible to solve the problems? Absolutely, but it may sometimes make it more difficult to visualize and see it. So we put it at A, and there will be no reactions in the y direction because it is free to move in the y direction at A, but the support is constrained at A in the x and z direction, and that's why we won't be able to move in the x and z directions. M sub A sub x and M sub A sub z are also shown here. Those would also be the reactions of the support. So altogether we have 5 unknowns here that we would like to solve for. So A sub x, applying the summation of forces in the x is 0. A sub x would be 0 right away. So this would actually drop out. Summation of forces in the z, A sub z plus F sub bc minus 80 is 0. In the z direction, we have these 3 forces. So we're okay there. Then summation of moment about y. We set that to 0. About y is given here. Obviously, the m sub a sub z, this is the y-axis. So we're taking the moment about the axis. In 2D, we take the moment about a point, but here we would routinely use moment about an axis. And in this way, obviously, m sub az, the a sub z and a sub x is not going to contribute anything to that moment if we take the moment about the y axis. Also, m sub a z and m sub ax, they don't contribute any moment either because the moment is not about the y-axis. So we actually pick the smartest axis to take the moment about. So pretty much 80 times 1.5. Of course, we again assume a direction. In this case, we assume this direction to be negative. Remember, we usually assume the counterclockwise to be positive, but again, that's pretty much relative based on the discussions that we have. So in this case, F is minus 80 times 1.5. F sub BC is upward, and we are taking the axis about the Y. That will be causing a counterclockwise moment. If you can see the sense of the moment itself, assume that the Y is fixed. We keep that axis fixed, and we're trying to pretty much rotate this portion BD about the y-axis. So if the force is acting upward, it has a tendency to rotate everything actually toward us. Kind of like bring this portion up to a point here, and as it gets rotated, it's actually rotates it in the direction of the y-axis, the way it's been shown. So if the rotation about the y-axis only, if this is the positive rotation, if this is the direction of the positive rotation, then that will cause a positive moment. And then as such, we can solve it. We can get F sub BC at 40, calculate that, and as a result, A sub Z would be 40. A sub Z is 40, and let's take a look at other unknowns. Let's write a scalar moment equation about point A. Again, that would simplify the analysis. We take the summation of moment about x-axis this time. This is the x-axis, okay? we have what we need to calculate the moment about the x-axis. The force 80 multiplied by 6, it's going to cause rotation about x-axis. And the other one is the F sub BC to 40, and that is also going to cause rotation about the x-axis. So we took care of these two forces. And the third one is the unknown, m sub ax. So setting up the equation as such, we would easily be able to calculate m sub a sub x 240 pounds, and for m sub z we has only m sub a z, and we pretty much there's no other force here that would cause any type of a moment about z. Okay, and if there were any forces in this direction, in the direction of the x, negative or positive, yeah, that would cause the rotation about the z-axis, but there is none here. So as such, m sub az is 0. Let's take a look at a concept quiz. Again, the rod AB supported using 2 cables at B and a ball joint at A. Okay, so there's a ball joint at A here, and there's also 2 cables at pretty much B here. They're connected at point B, but one is this cable, and one is the other cable that I just marked in red. Look at the condition of the supports at E and D, and try to determine how many reactions would be developed at E and D. And this is a 3-dimensional problem. Would it be any moments at E? Would it be any moment at D? The cables, they can really, they're free to rotate in that direction. Nothing would prevent them. So there would be no moment reactions at E and D. And at A, actually, there's no moment reaction. The entire structure is free to pretty much rotate, but they're not free in translation. So we're going to have how many forces here? Okay. Altogether, we're going to have 5 reactive forces, 5 force reactions, and that will be really the answer: 5 force reactions in this case. So if an additional couple moment in the vertical direction is applied to rod AB at point C, then what will happen to the rod? Remember, we're trying to add an additional moment in the vertical direction. Again, not a force, but a moment in vertical direction. And we try to turn it, and as such, the rod would become unstable because it cannot be restricted. Remember, there's no place on the structure that can restrict the rotation. So if we are applying a moment, kind of like trying to hold on to the rod and kind of like turn it in whichever way, this way, or the other way, or really whichever way, and there's nothing that would support it. It's going to take pretty much as we are applying the rotation, the entire structure is going to rotate with it. So it's going to be unstable since a moment cannot be restricted. So the answer would be D in this case. Let's do a group problem here. A rod is given here, supported by smooth journal bearings at A, B, and C. We assume that the rod is properly aligned, and we would like to find what the reactions would be at all supports for the load for the loading condition as shown. The plan is to draw a free body diagram, show all the forces on it, determine the reactions correctly, how many is at each support, and apply the scalar equations of equilibrium to solve for the unknowns. So closer examination of these joints, again, remember, it's given they are smooth journal bearing joints. As such, there'll be no moment, only reactions in whichever direction, depending on how they are constrained at, for example, point C, which is up here. They're going to be C sub Y and C sub Z. At point A, we're going to have A sub X and A sub Z. At point B, we're going to have B sub X and B sub Z, and 450 Newton, and the moment that's applied here on the structure is also shown. Those are external forces that are applied. We also show all the distance appropriately. So it is very important for us to examine these figures correctly and try to get a sense of their direction to reduce the likelihood of any kind of error in determining the reactions, and which may lead to the error in the calculation. So summation of forces in the y direction is 0. In the y direction, let's examine to see what kind of forces that we have. And the y direction is actually in this direction that I'm marking with red. This is the y direction. In that direction, we are going to have the y component of the 450 Newton force, right? This is the y component in that direction. We also have C sub y in that direction. So we need to take care of, we need to set up the equation with two of these unknowns, the y component of the 450 Newton and the C sub y, and no other forces or moments would be involved in that equation. That would really simplify the problem. Right away, we would be able to calculate the C sub I, the C sub y by setting up this equation. It's going to be minus 318 Newton. Now, don't change the direction of C sub y just yet. Hold on to it, carry the calculations, then you can do that at the end. Otherwise, you're going to run into problems changing it throughout the process, okay? So just carry this negative number with you throughout your calculations. That's a common mistake I've seen that people make. Summation of moment in the y direction. We set that to 0. Let's examine the free body diagram. In the y direction, we are taking the moment about the y-axis actually, and as you can see, A sub x and A sub z is not going to cause any moment about the y-axis. This is the continuation of the y-axis in the negative direction, but this is the entire y, okay, this direction. So what are the forces that could cause a moment about y? It's important to realize that there is a 300 Newton meter moment, external moment applied to that, so that would cause that. Would 450 Newton force, would that actually cause any moment, any rotation about the y-axis? No, it will not, because it actually go through y-axis itself. And what about C sub y? Would that cause any kind of a rotation about the y-axis? No, it wouldn't. So the only one here is really C sub z. If we apply C sub z, we need to multiply C sub z by distance 0.6. That would be the moment about the y-axis, okay? And in this case, it's going to be counterclockwise. If you position yourself standing right in front of a y-axis and looking at that, the direction of the rotation will be actually this way. It's going to be counterclockwise. So C sub z, and that's the positive direction. The assumption here is counterclockwise in the y direction is a positive direction. And then C sub z times 0.6 minus 300. 300 is actually applied clockwise. Is 0. As such, C sub z would be 500 Newton. What about the M sub B sub x? That still need to be calculated. B sub x is down here. We take the summation of moment about axis z at this time. This is axis z labeled here, actually upward to the page. The only two forces that would apply in this scenario and that actually would cause any kind of a moment rotation about z, axis z, it would be two of them. One would be actually B sub x. B sub x is right here, and it has a tendency to rotate the entire structure about the z-axis. So applying that's one way. B sub x is going to be cause that kind of a rotation about z-axis. There's another one, and that is what is it? C sub y, right? C sub y also has a tendency to rotate the structure about the z-axis. So as such, we would set those up, and B sub x would be turn out 239 Newton. Again, realize that we did not change the sign of C sub y. I carried that negative through, and I just accounted for the direction of the moment. Again, this is plus as counterclockwise. If you do it any other way, I guarantee you're going to make mistakes, and you're not going to get the answer correctly. And then there are three other reactions that need to be calculated, still need to be calculated. In this case, summation of forces would be, the summation of moment would be taken about the x-axis. X-axis is this axis that's shown here. This is the x-axis. You're going to take the moment about that axis. A sub x, A sub y doesn't contribute to that equation. B sub z would contribute to that equation. That's B sub z. It's going to cause a rotation about the x-axis. So B sub z is right here times the moment on point A. And the other components of the force are related to the 400 Newton. Remember, we are going to have two components to 450 Newton. One is vertical, one is in the z direction, and one is in the y direction. The one in the z direction would cause a moment about axis x, and the one in the y direction, this guy is also, I'm sorry, the z direction would also cause a moment about the x-axis. We set that equation up. There are also the 318.4. This is the 318 force that I just calculated in previous steps. That is our C sub y. C sub y would contribute that right here. It would, because it's going to have a tendency to cause a rotation. Also, C sub z would do the same thing. The magnitude of C sub z was calculated as 500, so that would also contribute to that. So we set up the equation, including all the terms. Summation of moment about the x-axis. We kept the best for last, and that was more involved, and there were more unknowns if you wanted to do that to begin with. So we had to calculate those unknowns first before we can actually set up the equation and solve for B sub z as minus 273 Newton. Make sure to check these calculations, and make sure to actually keep up with the calculations, and grab a calculator and check these numbers with me. Summation of forces in the x is 0. A sub x plus 239 is 0. And from there, A sub x minus 239 minus 239 Newton. Summation of forces in the Z is A sub Z minus 273 plus 500 minus 450. We just put all the components of the forces in the Z direction in that equation, set it as 0, and A sub Z would be 90.9 Newton. Let's take a look at an attention quiz before we can wrap the session up. A plate is supported by a ball and a joint, as you can see. Roller joint at point B, so there's a ball at A, okay, right here, this is A, ball at A, okay, roller at B, and a cable at C. How many unknown support reactions are there in this particular problem? It needs to be moved a little bit to the right, actually, there. Okay, so let's leave it at that. So okay, let's go back to the problem. So the answer, we need to find what the answer is. There would be one cable reaction of the cable at C. So that's one. This is a ball and a roller. We're going to have one more for the roller, again, depending on the direction there. It's free to, it's constrained in the direction of, in the Z direction. So we're going to have 2 so far for C and B, and there will be 3 for the pin at A in 3 different directions. That's in the Z direction, and there will be 1 in the Y direction, and there will be 1 in the X direction. So 3 plus 2 would be 5 forces for this system. So the C is the correct answer. What will be the easiest way to determine the force reactions? B sub Z, as I just mentioned in this case, B sub Z, that the reaction. Take the scalar equation, the summation of forces about Z, the vector equation, summation of moment about A0, set that to 0, scalar equations, and scalar equation summation of moment about Y, set that to 0. All these forces except B sub Z would go through Y, so that's actually the easiest way to set up a scalar equation about Y, axis Y, and set that to 0 would be the easiest and fastest way to actually get the answer. Let learning continue. This brings me to the end of this lecture, and if you have any questions, feel free to contact me.